Okay, welcome. So we're going to finish up our discussion of energy today, and one main topic remains, and that is the conservation of energy. So we'll get going on that. Basically, want to tell you kind of what's going on with this, and then from there we'll go through a couple of example problems using some that I've picked up, and then one of the homework problems as well. Okay, so first of all, what I'm going to start with is just the conservation of energy. Now, I'm going to make a note that really what we're dealing with in this context, the context of this class, is the conservation of mechanical energy. It turns out that energy is conserved for far more than just mechanical systems, but given that we're primarily dealing with mechanics, particularly right now, that is what we're going to focus on. And as a reminder, your mechanical energy, which I'll abbreviate as ME, this was equal to the kinetic energy plus the potential energies. Now we had our kinetic energy, and not to be confused, this is kinetic energy. That's not the spring constant, and the reason I say that is because the spring constant does come up when dealing with potential energy. But the kinetic energy is 1/2 mv squared. The kinetic energy. The gravitational potential is mgh, and the spring potential is 1/2 k delta x squared, where k there really, if it's hard for me to visualize the difference. Really, that should be a lowercase k. So this is the spring constant. Don't confuse the k in the mechanical energy formula with the spring constant. They're not the same thing. Um, Okay. So the idea here, behind the conservation of mechanical energy is that if there is no work due to non-conservative forces, and as a reminder, the non-conservative forces were basically everything but the gravitational force and the spring force, basically the two forces associated with those potential energy. Um, Mechanical energy will remain constant. Okay, that is basically what the conservation of mechanical energy is saying. So the idea here is that to state this mathematically, if your non-conserved work, so work with a subscript NC for non-conserved is equal to 0. Now, to just briefly discuss what I mean by non-conserved work, basically this is work done by something like an external force, an applied force like from an engine or a person, could also be due to friction or drag. These are all non-conservative forces. Um, if your non-conserved work is equal to 0, then your change in mechanical energy will be equal to 0 as well. So the idea here is that we have our initial mechanical energy over here, and that's equal to 1/2 mv initial squared plus mgh initial plus 1/2 k delta x initial squared. So that's all your initial mechanical energy. So I should put that on the top, shouldn't I? So that is your initial mechanical energy. Basically, what we're saying is that this is going to be equal to your final mechanical energy, which is the same stuff, just taken at a different time. So it would be 1/2 mv final squared plus mgh final plus 1/2 k delta x, not initial, but final squared. Okay, so that would be your final mechanical energy. Okay, and the main idea here is that your mechanical energy, if you're not having energy added or removed via work, basically what your mechanical energy, what it'll do is it will get transferred between these buckets. So you might have initially some spring energy, and then that might get converted into kinetic and potential, and then that might get converted back into kinetic. So I'll give you an example of that, like on a pogo stick. Um, and I'm just going to try and indicate this, what we've got. So we've got the stick, and then there's a little spring around it. And, you got a person. on the pogo stick, holding on. And initially at step one, um, it's the spring is compressed. Okay, so it's also at some h equals 0, so it's at ground level. So the spring gets compressed, and right here, all we have is we have u sub spring. Okay, because the spring is definitely compressed, and basically the idea there is that at that point, you have the spring, and for a pogo stick, it's a pretty strong spring, pretty stiff spring. Um, and then you find its potential energy that way, but person is also not moving. So this kinetic is equal to 0. Call that K1. We could call this UG1. That is also equal to 0, just because the height, we generally take, the ground level to be 0. Um, that would be fun. Then what happens if this person, goes and they go up and they do this kind of arcing path, so they become a projectile after they leave the ground. Well, at the top there, our u sub spring 2, that is now 0 because that spring is no longer extended. But this kinetic energy 2, well, this is 1/2 m whatever the speed at that point is. And this might be the top of the flight, but he's still going. He's still got some forward motion, some rightward motion, as this picture is drawn. So he's got some kinetic energy there. But he's also got some height. So we could say, okay, there's some height here. So we would also have some gravitational potential energy, that would mgh2. Now, if he continued, right before he hit the ground, and that would be 0.3 right there. This is before the spring coils again, so the spring potential is still 0. But now the kinetic energy basically has everything. So it's 1/2 mv3, not cubed, squared. Doesn't become cubed. So it's still squared. And this would be u sub g would be mgh3. And if it's right before it hits the ground again, then he's back to 0. Okay. So the idea here behind conservation of mechanical energy is that the total amount, so this would be me1, this would be me2, this would be me3. These three would all be the same. That is what conservation of mechanical energy is saying. And as energy transfers from one category to another, you can learn different things about the system, like how high the guy goes, how fast the guy is going. Okay, so you can learn all these things about how that is going. Okay, so that is that is something that you can do there. Now, to kind of extend this a little bit, and this is where it comes in more often, is that if your conserved work is not equal to 0, so if you do have some external agent doing work, then basically what that means is that that non-conserved work is equal to the change in your mechanical energy. So any work done by a non-conservative force will either add mechanical energy to the system or it will remove mechanical energy to the system. So an example of a non-conserved force adding energy to the system: an engine increasing the speed of an automobile or a boat or something. We're going to do one with a boat. That would be an example of a non-conserved work adding energy. So it could increase the speed without changing any of the other energies, which means mechanical energy got added to the system. Another example of decreasing mechanical energy would be friction slowing an object down. In that case, friction is actually removing mechanical energy from the system, okay? But in that case, either one is a non-conserved force that is changing the mechanical energy of the system. So you can use the conservation of energy to figure out how much work non-conservative forces have done, okay? So that's the other main way that this gets applied. And that is kind of what I want to show you with one of the, well, a couple of these example problems. One already has the answer, so I'm just gonna kind of step through it. But I need to put it in here first. So is that gonna work? Okay, good, that worked. All right. All right. So in this one, basically what we have here is we have the velocity of a tugboat increases from 2 meters per second to 4 meters per second in the same direction while the force is applied to the tugboat for 20 seconds. Turns out this 20 seconds is irrelevant information. We only care about the energies. Now, the idea here, what this graph wants you to do, it wants you to give a representation of the kinetic energies before and after, and then also the work that had to be done in order to get those kinetic energies. All right. So that is what we're going to be looking at here. Now, if we take a look at this, what we could do, we could, calculate kinetic energy. So we could do, for this one right here, 1/2 mv initial squared. Now we don't know m, so we're gonna have to leave m just as a symbol there, but it's okay, because we do have the speed. So we have 1/2 times m times 2 squared. So it turns out that this is equal to 2m. So, and then we can look over here that this 2m of energy is equal to 2 bars. So what we can say is that each bar equals 1m of energy is basically what we're saying. Okay. So initially we had 2 bars of kinetic or 2m of kinetic energy, and that corresponds to 2 bars in the graph. So what I could do then is I could look at the final state, and I could say, okay, K final is equal to 1/2 m V final squared. And then that's equal to 1/2 m and then 4 squared. Well, 4 squared is 16 times 1/2 would be 8m. So basically, this means we've gone from 2m of energy to 8m of energy, which means that this should be 8 bars. Now, the key is already done, and you can already see that. It's already drawn in the 8 bars. You can count those 1, 2, 3, 4, 5, 6, 7, 8. 8 bars of mechanical energy there. Okay, or kinetic energy there. All right. Now, the idea behind the work bar, basically, this is the energy added between final and initial. Okay, so that is what you're doing. That's why there are 6 bars there. So we had 2 initially. We needed to add 6 to get to the final number of bars of kinetic energy, which was 8. Okay, so this is a situation like what we were just talking about, where the non-conservative work, basically the work done by the tugboat's engine, had to make up for the difference in the mechanical energy at the beginning and the mechanical energy at the end. There's only one type of mechanical energy here. That's kinetic. There's no gravitational, no spring. There's no change in height for gravitational. There's no springs to do any work like that. So that's all we're dealing with here. Okay, so that is what is going on with that one. All right. For part B, this is a very similar sort of thing. And it says, okay, what we did here is it's going to the right. It's going just as fast, but in the other direction. Now it turns out the graph, what we have here is actually no different. Okay. In that basically what happened is there was some initial kinetic energy, there's some final kinetic energy, and the engine was responsible for that change. However, what this doesn't really account for is that, particularly if this is all one-dimensional, is that basically what this engine would have had to do in order to, first would have had to slow this down, so it would have had to remove all the kinetic energy when it brought it to the stop, and then add the kinetic energy back when it reversed it. So that would be the main difference if you looked at intermediate steps. But this problem isn't asking you for that. It's just asking you for the initial and the final. And the kinetic energy final doesn't change. Like it's exactly the same. Even though direction has changed, remember, kinetic energy didn't depend on direction. So we only care about the speed. The speed is the same in both of these two problems, which means that they have the same initial and final kinetic energy, which means the total work in both cases had to be the same. All right, so that's the main thing about that one. All right, I want to do I want to put it's fine. I'll put another one and give this one a shot. See if you can, I'd encourage you to pause this, see if you can do this on your own. There are more options here because no initial bar is given. Now there's one way that I think works pretty well to do this, but yeah, like I said, give this one a shot on your own. So what I would do is I would say, okay, I'm going to look at this one, and that's my initial kinetic energy, and that's 1/2 mv initial squared, not v final. For what it's worth, it might be worth saying that both your spring and gravitational potential energies are going to be zero. So that's fine. Just the only mechanical energy that's relevant here, mechanical energy is going to be equal to your kinetic energy. Um, they are equal to zero. It's not that they're not equal to zero, but they don't come into play. All right. So what we have here is we then have 1/2, and this time we are given the mass. It's just two. The 1/2 and the two cancels out. That's kind of nice. And then we have 4 squared, which is going to mean that we'll have 16, and we can just do 16 joules there. Now, the question of how we represent this is it's kind of up to us. We obviously can't do 16 because we only have, I think, 9 bars here. So it'll be easier if we find the final kinetic energy to see how this is going to work. So 1/2 m v final squared. So 1/2 times 2 times 6 squared. And when you do that, that'll give you 36 joules. Now we need to figure out how to display this on the graph. Okay. And basically what I would do here is I would say, all right, what I'm going to do is I'm just going to let 1 bar equal 4 joules. That seems pretty reasonable because then this thing is 4 bars and this one would be 9 bars. Okay, so I can do that fairly straightforward. Do a 4 bar right there and a 9 bar. There are only 9 here. So we can do that. And then the idea is that the work has to account for the difference. So we went from 4 to 9. We need 5 in here in order to make up for that difference. So it's basically these two are combining to give that one. All right. Now, an alternative could be, what if instead of 6, this thing was actually 2 meters per second? Okay. So we're going to change that up slightly. Now, if instead it was 2 meters per second, we find that K final, I'll do this in red just to indicate that we're doing it. We'll leave the initial the same. But if the K final was 1/2 mv final squared, this would then just be 1/2 times 2 times 2 squared, which would be 4 joules. And now this would then be 1 bar. So instead of having, this 9 bar thing, what I would have here is just 1 bar. No, I'll even fill that in. Okay, so that's for the red situation. Now, what we need to have happen is we still need to have the initial plus the work equal the final. Okay. Now, the only way we can do that is if instead of having work add energy to the system, we have work subtract energy from the system. And in this case, what we would do here is we have to go from 4 bars to 1 bar. And we do that by bringing 3 bars out. Okay. So we take 3 bars out. And then we have the combination of these two to give us this third one. Okay. So that is basically how that would occur. All right. So that's what's going on with this one. So there is a problem kind of like this in the homework. So you can be sure to take a look at that. The last thing I want to do is talk about one of the homework problems because I think it's actually a pretty good example of how to use both the conservation of energy and power, which was a topic of the last um of the last lecture. Sorry, to make a note of something I need to change. So what 19 is saying is it's saying a motor, I'm gonna just paraphrase, it lifts a 2,500 kilogram, it's an elevator motor, so with that, lifts a 2,500 kilogram car, 35.0 meters in 12 seconds to a height of 35 meters, obviously. Don't need to write that. And increases the speed from 0 to 4.00 meters per second. Okay. So, and then the question is, what is the power of the motor? All right. So this is something we're going to have to take a look at. We need to know, not only how to use power, but we need to also know, we're going to need to do some energy conversion here because there are going to be multiple forms of energy. Okay. So in this case, power, what we're going to want is we're going to want the power is going to be the work done by the engine over delta T. Now, when you see this work done by the engine, one of the things you might realize is that oftentimes what this is going to be some non-conservative work, which means it's going to be equal to the change in mechanical energy. Okay. Now, it's worth knowing that what kind of mechanical energy changes in this elevator. And you can just list this qualitatively. The first one that's obviously changing is the kinetic energy. All right. And the whole idea is that our initial kinetic energy is equal to 0. And that's just because our initial velocity is equal to 0. And then we have some final kinetic energy, which is going to be 1/2 mv squared. All right. And we know that that's going to be some value. But we also have a gravitational mechanical energy, gravitational potential energy change. And our initial gravitational potential energy is going to be 0. And that's just because the initial height is 0. But then our final is going to be our UG final is just going to be MGH. Okay. So we need to find all of these things. All right. Now, the delta mechanical energy, basically, it's going to be your final mechanical energy minus your initial mechanical energy. This is just equal to 0. And basically that's because both of these two were equal to 0. So your change in mechanical energy is just going to be your final kinetic plus your final gravitational. Both of these things have been added to the system. So we should find those. Final kinetic, 1/2 mv final squared. This will be 1/2 times 2,500 times 4 squared. That'll be 8 times 2,500, which would be 20,000 joules. And then your final gravitational is going to be MGH, which will be 2,500 times 10 times 35. And that will be 2,500 times 350, which just verify this. Again, using G as 10. You could use it as 9.81. It'll be a bit off, but not a bit off. It'd be different. Like I said, using it as 10 is not bad for an approximation. So this will be 875,000 joules. So your total mechanical energy, I'm sorry, would be the combination of these. And that's going to be 895,000 joules. Now, what that means is that is your work, and that is what you're going to use in your power formula. So power equals 895,000 in the numerator, and then delta T in the denominator. And we're just given delta T. It said this happened in 12 seconds. So that's the thing we use. And when we divide this by 12, we end up with 70. Hold on. Yeah, end up with 72,917. I would probably just call this 73,000. And the units again are joules per second, and joules per second is going to be a watt. So keeping 2 sig figs becomes 73,000 watts. All right. So that would be it for that one. If you use 9.8, you probably got something a bit higher than this. Probably, yeah, probably something a little bit higher, I would imagine. In any event, or would it be lower? I think it might be lower. Yeah, you would have got something a little bit lower than this. In any case, um, oops. Oh no, that's incorrect. I was reading that. I typed in the wrong thing. Okay, I thought that was wrong. This would actually be 74,583, which again is about 75,000 watts if we only keep 2 sig figs. So, or you could do 74,600 if you wanted to keep 3 sig figs, whatever. But that is the number of watts in this thing. So that is how you would look at number 19 in the homework. So hopefully that makes sense. But I am going to go ahead and stop this recording here. Hopefully that gives you what you need to complete all the energy problems. We'll be getting into momentum, which will be our last topic in mechanics and the last topic before the last topic of the midterm we'll cover. So thank you for joining me today. I will see you next time.